Welcome to the deep dive. Today we're tackling a really high-stakes decision in manufacturing. It's something that can keep machine shop owners absolutely paralyzed.
Hmm.
How do you choose the right spindle head for profile machining?
Mm.
We're looking at the foundational choice between, the cutting-edge, super complex five-axis head
Right.
and the much simpler, more cost-effective add-on, the angular head.
And it is a genuine dilemma.
Hmm.
This isn't just about buying a piece of hardware. You're making a decision that, really, it dictates your shop's capability for years to come.
Oh, for sure.
You make the wrong move, and you either drain your entire capital budget on something that's just overkill, or you find out mid-contract that your shiny new equipment just can't handle the job's geometry.
And then you're facing rejected parts, massive delays.
Exactly.
I think the biggest trap here, and we see this a lot, is the assumption that, well, since both tools cut from the side of a profile, they must be functionally interchangeable.
And that's a dangerous assumption.
If you go and spend top dollar on a massive, dynamic five-axis system just to drill a few simple side holes into an aluminum extrusion, you've completely misspent your money.
And conversely, if you try to force a simple angular head to machine a dynamic curved surface, say a twisted structural beam for a piece of architecture, you are guaranteed to ruin the material.
So our mission for this deep dive is to establish that single guiding principle.
It all comes down to one thing. The right choice must always, always match the specific geometry of the workpiece.
Okay, so let's break that down. If my geometry is intricate, multi-angled, or needs continuous contouring, where do I land?
Then you are firmly in the camp of the five-axis head, no question. It gives you the versatility you need for those complex 3D surfaces.
And what if the workpiece is, standard? It just needs some fixed angle operations like side drilling or a few simple slots.
Then you choose the fixed angular head. It is the definition of cost-effective simplicity, especially when you're trying to squeeze extra capabilities out of a standard 3-axis machine you already own.
Okay, so to really understand this, we have to get into the mechanics to see why these two tools, which, they look superficially similar.
But they operate in fundamentally different universes.
Yeah.
Okay, let's unpack this.
Let's start with the dynamic one, the five-axis head. You said it allows for fluid, continuous motion. How exactly does that articulation work?
Think of it as truly articulating. If a standard spindle is like your forearm, it can only move up, down, left, right. The five-axis head is the integrated human wrist.
Ah.
It uses two key rotational mechanisms. We call them the A and C axis. The A axis provides the tilt, which lets the tool lean side to side, and the C axis provides the swivel, or the rotation around its own center line.
So those two axes, A and C, that's what allows it to position the tool at pretty much any compound angle you can think of relative to the surface.
Precisely. And the key thing isn't just that it can position the tool at an angle, but that it can do it simultaneously with the linear X, Y, and Z axis.
That's the five-axis linkage you mentioned?
That's the linkage. It creates a continuous, uninterrupted toolpath. This is absolutely vital for maintaining the perfect cutting angle across a highly curved surface. Imagine milling a complex pocket into an engine manifold.
Oh, like an aerospace wing spar.
Perfect example. The head never has to lift off the part, stop, or reindex. It just flows over the surface, like water.
That dynamic, real-time adjustment sounds incredibly powerful. Now, how does that compare with the angular head? You called it a rigid adapter. If the five-axis is the wrist, is the angular head more like a fixed elbow?
That's a great way to put it, yeah. The angular head is mechanically rigid. It's an angle adjuster, plain and simple.
Okay.
You insert it into your main spindle, and it locks your tool at a set angle, usually 90 degrees. It basically turns your vertical machine into a horizontal one for side access.
So it's static. What if I need to change the angle of the cut, even just a little bit?
You can't. Not while it's running. You have to stop the machine, physically loosen the adapter, rotate it, relock it, and then restart the program.
Or just swap out the whole tool?
Or, more commonly, you swap out the entire tool assembly for another one that's preset to the new angle.
Yeah.
It simply cannot handle any geometry where the surface angle changes during the cut.
So like a curve that wraps around a corner? Or...
Exactly. Or a chamfer that needs to follow a variable pitch. It's fundamentally limited to orthogonal machining, straight side drilling, or fixed angle face milling. That's it.
That clarifies the mechanics perfectly. So the five-axis head is all about flexibility through continuous dynamic linkage, whereas the angular head provides access through fixed rigidity. But for most shops, the conversation quickly shifts from capability to cash flow.
Absolutely. And this is where the angular head becomes an extremely attractive solution for I say maybe 80% of profile machining needs.
Because it's an affordable accessory.
It's an accessory, not a foundational machine component.
So if a shop is dealing with, say, high-volume production of standard parts, thousands of identical window frames that just need lock holes drilled in the side, the angular head is the clear winner, just on cost and efficiency.
Precisely. It lets you take your existing, affordable 3-axis machines and immediately enable multi-sided machining. You don't need that huge capital investment. And think about the setup time.
Right.
If you're using a basic 3-axis machine for that job, every time you need to machine a different side of the profile, what do? You have to manually flip the workpiece.
Unclamp it, flip it, reclamp it, reestablish your coordinate system.
And every time you do that, you're introducing a little bit of positioning error, not to mention eating up precious operator time.
That handling time just kills your efficiency on high-volume, repetitive jobs.
It does. With the angular head, you clamp that long profile once, you run the entire program, accessing 3, maybe 4 different faces, and you walk away. It's the ultimate set-it-and-forget-it multi-phase solution on a 3-axis budget.
And you save a ton on fixtures.
Massive fixture cost savings. Now, compare that flexibility, that ability to buy it later, to the 5-axis system.
It's a different world, isn't it?
Completely. A true 5-axis head is a heavy investment, both financially and structurally. It needs a specific, really robust machine structure.
Yeah.
And because of the precision alignment and the complex wiring for the A and C axis, it's almost always configured at the factory.
So you can't just bolt one on later.
Trying to modify a standard 3-axis machine later on to accommodate true 5-axis simultaneous motion it's usually extremely difficult, if not entirely impossible. It's a huge initial outlay.
So the angular head is a smart, incremental investment. You buy the capability when the contract demands it.
Exactly.
The 5-axis is a complex, all-in foundational investment you have to commit to from day one.
That is the core budgetary difference. But we haven't even touched on the biggest hidden cost yet.
Which is?
The non-hardware expense, the software and the people.
Ah, okay, this is where it gets really interesting. Our source material is very clear on this. Having a state-of-the-art 5-axis machine is, well, it's pointless if your staff can only write basic 3-axis G code.
Right. The brainpower investment.
So talk about the programming complexity.
It's astronomical compared to 3-axis. First, you need expensive, advanced CAM software, computer-aided manufacturing software. And then you need highly specialized programmers who can manage something called RTCP.
RTCP, Tool Center Point. That sounds like pure calculus. What is it actually doing in, plain English?
It's collision control, mostly. Imagine your tool is tilted at, say, 45 degrees, and the head is swiveling around dynamically as it moves.
Oh, okay.
The physical housing of that spindle head gets awfully close to the workpiece. If the machine isn't constantly recalculating where the actual tip of the tool is relative to the part in the tilting head,
you're going to gouge the part.
You'll gouge the part, or worse, you'll crash the very heavy tool holder right into your material.
So the RTCP algorithm is the safety net. It makes sure that when the head tilts, the tool tip stays exactly where it's supposed to be, no matter how the head is rotating.
Yeah.
It prevents the machine from crashing itself.
Exactly. And managing that coordination, that synchronized movement of all 5 axes, while accounting for nonlinear error checking, it requires incredible skill.
And those programmers are hard to find.
These experienced 5-axis programmers are rare, they are highly sought after, and they command very high salaries.
And that introduces what we call key man risks for smaller shops, right? If you only have one person who understands your custom post-processors and can debug that complex RTCP code,
your entire operation grinds to a halt if that person leaves. It's a critical vulnerability. The personnel cost and the software license fees can easily outweigh any savings you thought you were getting. It's a massive commitment.
Now let's go back to the breath of fresh air, programming the angular head.
Oh, it's utterly simple by comparison. Since the angle is fixed, let's say it's 90 degrees, the programmer is essentially just dealing with standard 3-axis linear movements.
So what do they do differently?
All they have to do is tell the CNC system, with a simple macro or a geometric compensation, that the tool is sticking out sideways, and they account for the physical length of the head assembly.
So the machine is just dealing with known fixed offsets, not these continuous dynamic recalculations in 3D space.
Precisely. You can use much simpler, more common CAM packages. And you can rely on a much broader pool of machining talent. You save substantially on specialized training and salary demands. That is a huge factor for shops trying to grow.
That simplicity of staffing versus the rarity of high-cost specialists it's a truly underrated deciding factor.
Okay, Let's pivot now to applying this on extra long profiles,
Mm-hmm.
because this presents unique physical challenges. We're talking 6-meter, even 10-meter structural beams, where material rejection and surface finish issues are just amplified by the sheer length.
Long profiles are always challenging. The material itself can be less stable over that kind of length. But again, the geometry dictates the choice.
When does that extreme length absolutely demand the 5-axis investment?
If that massive beam needs anything complex, a twisted shape, an architectural 3D contour, a complex groove that has to transition along the length, the 5-axis is the only way forward.
And it's also about surface finish, isn't it? It is. To get a good surface finish on a curve, a 5-axis head can continuously tilt. This lets it use the side of a ball-end mill, which creates a much smoother surface. It avoids those rough, noticeable step-over marks that a 3-axis machine would leave trying to approximate that same curve.
And crucially, on a really long part, you want to eliminate reclamping.
You have to. The 5-axis head allows you to machine up to 5 sides of that massive beam in one setup, in a single coordinate system.
Which ensures precision along the entire length.
It ensures absolute precision. You eliminate the cumulative error that you get from manually moving and reclamping a 10-meter profile multiple times.
But what if that long beam is simple? A massive aluminum extrusion for a standard door frame that just needs some side holes and straight slots. Is the angular head still the smarter play?
Absolutely. If the geometry is simple, the angular head allows a shop to buy a long bed 3-axis machine, which is far more accessible financially, and use it effectively for that side access. You completely avoid the monumental investment of a true 5-axis gantry system built for 10-meter parts.
But there's a risk. Using a rigid adapter on a long profile introduces a specific mechanical risk, right? The tool length to diameter ratio.
That is the crucial caveat.
Yeah.
Yes. Because the angular head is a rigid fixture sticking out from the main spindle, it acts as a leverage arm.
Okay.
If you have to use a long tool, that length to diameter ratio gets worse very quickly. The whole system becomes much more susceptible to vibration, to chatter, to deflection.
And that just destroys your surface finish.
It destroys it.
Yeah.
So users have to manage that very carefully. But for simple tasks like drilling side holes or straight slotting, the angular head provides essential side access without the complex programming or the need to reposition the beam constantly.
This deep dive has done an outstanding job of showing that the answer to this hardware dilemma is, well, it's never a blanket, buy the best technology.
Yeah.
It is always about matching the tool's core functionality to the complexity of the geometry you are trying to produce.
That is the ultimate takeaway. If you need dynamic, continuous motion, complex curves, high precision across massive parts, you invest in the 5-axis head and, just as importantly, the staff to run it.
Right.
If your needs are fixed angle, simple side operations, and if budget and training simplicity are paramount, the angular head is the clear winner. The decision hinges entirely on the shape of your finished workpiece.
So here's where the analysis takes us, building on that insight we've gained today. We established that for 5-axis systems, the largest operational costs are the advanced CAM software licenses and finding those rare, highly skilled programmers who can manage complex coordination like RTCP. If that shortage of specialized staff is the single biggest barrier preventing small and medium-sized shops from adopting advanced manufacturing, how might future machine control software evolve? Perhaps using AI-assisted programming or dramatically simplified interfaces to handle those complex tool center point algorithms automatically. Could software democratize these complex machining capabilities, making 5-axis precision accessible even to a shop running a 3-axis budget? That's a critical challenge for the future of manufacturing and something for you to mull on as you plan your next shop upgrade.